I'm starting it now. Um, I will, after class is over, I will send you all of the PDFs of the notes, all of the video recordings. Um, so the last thing that we did last time, and I'm actually going to erase something that I did in haste and draw it again, is we saw that for our solution to the Schrodinger equation to make sense, the terms in the Schrodinger equation had better not blow up. So that means that um, the second derivative of psi must be finite. And that's true only if both psi and the first derivative of psi are continuous, because the derivative of a discontinuous thing is infinite. The one exception is that if um, the potential is actually infinite, then you can have a discontinuity in the first derivative of psi. So we'll actually need that in a moment, but I'm just going to write it down here. If the potential is infinite, then that can cancel a discontinuity in d psi by dx. Stick that in the back of your brains. We'll use it again in a moment. Okay, now I'd like to do our first example. And then that example is as follows. We're going to wind up graphing uh, potential as a function of position. So I want to imagine a system like this, where on the vertical axis I am plotting the potential as a function of position. Actually, we're using u. And here is position. So I'm going to think about an axis that just extends this way a little bit. So this potential, oops, u of x is infinity for x less than 0, 0 if x is between 0 and L, and infinity again for x greater than L. So the potential, basically an infinite potential means that a particle would have to have infinite energy to go into that region. So we're going to exclude this region from our particle, and we're going to exclude this region over here from our particle. That's L, and confine our particle only to move in that region below. So this potential is called the infinite square well. It's infinite. This is because v goes to infinity, and that it is square because v equals 0 inside. So we have a particle that's basically a free particle, but it's trapped. So what we'd like to do now is to solve the Schrodinger equation for this setup. Give me 1 minute to click on something on my end. Not that, that. Okay, so remember the Schrodinger equation that we have is minus h bar squared over 2m times the second derivative of psi plus the potential term equals a term over on the right that we identified as the energy times psi. So now our task is to find a function psi of x that solve this. Now, one of the things that we see right away is that we have this green piece here. So what is u of x outside the well? What is u of x like for x less than 0?
Infinity.
Infinity, yeah. So if u of x is infinity, what does psi have to be there to avoid something going wrong?
0.
Exactly. So um, where u equals infinity, psi must be 0 to avoid badness. All right, so now our function is constrained. We're going to go back up to our little doodle. Actually, I'm going to copy paste this. Give me a minute to, I can do it this way. So I think I can select all of this. I'm new to using a tablet. So I think now I can go down here and hit paste. Blurp, there we go.
Could you go over why there's no time dependence in that equation again?
Why there is no time dependence? Absolutely. So what we did, going back up, a way back, this is kind of a review of what we've been doing since I've been here, is the first assumption we made is that the wave function's dependence on both space and time is separable, right? That it's a spatial piece times a time piece. And we said, now let's think about the two of them separately, right?
Yeah.
And we saw that in the cases where it's separable, that those are describing stationary states that have this form. The thing I just drew the green box around.
Mm-hmm.
So the full wave function, depending on time and space, is the spatial part multiplied by a part that depends only on time.
Oh, and then those e's canceled. Oh, I see that in my notes.
Yeah.
Like further down?
Where we looked at the probability density, then yes.
Yeah.
But what we're doing here is we are now thinking about only the spatial part. Let me make a note of this. So this is, whoops, I'm on the wrong tool. So here we're concerned only with the spatial part. I think it's kind of unfortunate that we are using both psi for the full thing and just the spatial part. That's why I'm always writing psi of x, because then once I have the spatial part, I have psi of x, the full thing, psi of x and t equals the spatial part, which we're about to figure out, times the time part, a e to the I energy over h bar times t. Does that help, Caitlin?
Yeah, thank you.
Sure. So here I'm only thinking about the spatial part. And what I realized is that it's got to go to 0 here and here. So now what I want to do is I want to think about what function psi of x solves the Schrodinger equation inside the potential well. So now we've got minus h bar squared over 2m, second derivative with respect to x. There's no potential here, equals e psi of x. So here, inside u equals zippo. So now what I want to do is I'm going to divide both sides by minus h bar squared over 2m. So that gives me the second derivative of psi equals minus 2me over h bar squared times psi of x. So now we have to be a bit clever. We're now in a situation where taking the second derivative of psi gives me psi back, multiplied by that term minus 2me over h bar squared. So Nick says, does that give another complex solution? I'll ask you all, what functions have this property where when I take a second derivative, I get back the same thing multiplied by minus some junk in front? Cosines and sines, or okay, stand by for 1 second. Isa just sent me a message saying that her internet has died. I'm going to get her the guest link to the Collaborate session. Stand by 1 moment. I'm not sure exactly what situation she's in, but I want to make sure she can get back in. All right, email sent back to Isa. Okay. Yes. So in the meantime, everybody has said either complex exponentials or sine and cosine. Remember, two derivatives of sine. First derivative of sine gives you um, cosine. Second derivative gives you minus sine again. Or complex exponentials. We're actually, both of them are solutions. And we'll actually take a look at both. Um, so they're either psi of x equals some constant times a sine or cosine of kx, or psi of x equals a e to the minus I kx. Now, each derivative that I take is going to bring down a factor of k, right? So, as a sidebar, we need to ask what k is. What is k? So, let me take the second derivative of a sine kx equals minus a k squared sine kx. So k equals the square root of this stuff here that I'm outlining in blue. So k is, we're going to go back to brighter type for this. This will be important. K is the square root of 2me over h bar. Okay. So now, looking at the potential well, can I still paste it in here? Nope, that's the guest link. Looking at what I know about the potential well here. Can you tell me if I want sines, cosines, or complex exponentials? You told me it's either sine or cos, but in our problem, which of those do I have? So James votes complex exponential. Why do you say that? Matthew votes just sine. So James and Matthew, could you type out the reasoning behind your choices there? James, I'm jealous that you get a profile picture, especially one by a lake or a beach. I need to make one. It's where you wish you were right now. Yeah, Alice is out on like a 50-mile bike ride. I'm so jealous. She's out riding in the sunshine. But being here with you all is pretty fantastic too. But I wish I was teaching class out in the sunshine. So Matthew's reasoning is right. Matthew says that I want sine and I do not want cosine because sine of 0 is 0. And that is the boundary condition. Um, so pasting again this thing, we're going to keep looking at it. So now I know what I have figured out is that psi of x is some amplitude times the sine of um, kx, where k we know is the square root of 2me over h bar. Is everybody with me so far? James, it turns out we will do complex exponentials again in a bit. Um, does anybody want to ask questions or ask for comments before we talk about what k is? I'll pause for 15 seconds, 30 seconds, and give you all time to type.
So is k the wave number?
Yes, k,
Okay.
yeah. So, sorry, thank you for asking that.
Yeah.
So k here, when I said that the solution is this times kx, this is the wave number. And remember, wave number is the number of wiggles per meter. So sine kx gives me a sine wave with k wiggles per meter. Does that make sense?
Gotcha. Yeah.
So that's why I've used that letter. You might say, well, we just pick k as an arbitrary constant. But here, this is the wave number.
Okay.
What happens with the other
Yes.
boundary? Exactly right, Nick. So what do you think happens? Yep. So we must, actually, I'll write it this way. We can only have values of k such that the other boundary also has psi of L equals 0. So what I've got is I have now sine of KL equals Zippo. Should it also end on a downward slope of sine equals 0 for L? Yes, Charles. So what you are telling me, in effect, and here I'm going to make this bigger, is that the allowed wave functions look something like this. So one of them, oops, so this is going to be maybe tricky for me to draw on my tablet. I'm just going to have to zoom in a lot to make sure I get my drawings right. Let's see, that's about the halfway point. So you're wanting me to draw something like this, right? So here, um, let's draw the pictures first. So Charles, I know you have seen this before with me twice because you took both physics of music and Physics 307. The reason that we emphasize this, the reason that this is so profound in the acoustics concept, like thinking about guitar strings, is because that's the same solution as here. So Charles, if this is looking familiar to people who took physics of music or who took Physics 307 with me, the reason I emphasize this idea there is because it's the same solution as this. Um, give me 1 second. I need to do something for the physics clinic. Um, I will be back in 10 seconds. There's something that I have to set up. I'm supposed to start the physics clinic every day at 1 o'clock, and someone just pointed out to me that I had not done that. So that's fixed. Sorry about that. So the other solutions are sine waves that also obey those same constraints, right? I have to draw sine waves that, let's see, that's not right. That also go to 0 on both ends. These dots that I'm drawing are just guides for my own terrible art. Let's see, go up. There's a node there. That's not quite right. I'll get that better. So let's see, this goes down, has a minimum there. Drawing this is harder on a tablet. Like, I got good at doing this on a blackboard, but this is trickier like this. All right, now let's fix the one I just deleted. Down, down, up. You get only 3 drawings because I'm going to mess up the rest. But you see the pattern. So let's figure out what K is. So if sine KL equals 0, that means KL equals n pi, where n is an integer. And then this tells me K equals n pi over L. Everybody with me so far? Or are there any questions? Okay. So what this does... Oh, go ahead.
Excuse me. Why is there a k in the sine function?
Why is there k in the sine function? So back here, when we were originally thinking of solutions to this differential equation, where when I take the second derivative and what I get back is the same function I started with multiplied by 2me over h bar, the suggestions were sines and cosines. So a sine, like a generic sine, is amplitude times sine of something times x, right? So you've often seen generic functions like, and I'm going to scroll down here. So you've seen something like f of x equals a sine omega t, or f of x equals a sine kt, right? This is like a generic sine. And, whoops, kx. The reason we use omega and k here is omega is an angular frequency. That's what we use that letter for. And this is angular frequency, and its units are, whoops, sorry, I palmed my touchpad. Give me one moment. The units of omega are something like radians per second. K is the same thing, except instead of describing how fast something oscillates in time, this describes how fast something oscillates in space. So rather than calling it, so I prefer to think of wave number as like spatial frequency. Um, and that's a term that you'll actually see in image science a lot. It has units of not radians per second, but radians per meter. So initially, when we realized that sines and cosines would be solutions to our differential equation, we just used k here because that's kind of the generic idea of like how fast does something oscillate with time. But then we realized that only certain wave numbers are allowed because we must choose k such that the wave function psi goes to 0 on both ends of the well. Eva, I'll get your question in a moment. So then we said, all right, k is not just some like abstract thing that says, okay, a sine wave wiggles so and so fast. It can take on only very specific allowed values in this problem. So now what we are doing is we're saying, okay, let's try to understand which values of k are allowed such that when I put them in psi of x equals a sine kx, I have the boundary condition that I need for this thing to go to 0 on both ends. Does that answer your question, Danielle?
Yes, makes much more sense. Thank you.
Sure. Ava asks, what does it mean qualitatively for the particle to be in a well? Good question. So this analogy is to like a real well, like the kind of thing that you store water in. So a well is a region of lower potential energy than its surroundings. And that's what we have, right? We have a region whose potential energy in the middle is lower than the potential energy on either side. Um,
I guess I'm sorry, I'm just kind of asking, is this like an orbital or like
mm,
electron would be found a distance away from the nucleus? I'm just trying to visualize it.
you're trying to visualize like what kind of physical situation would correspond
Yeah,
to this.
yeah.
Great
Thanks.
question. So there's one in your homework where you're imagining an atomic nucleus where you have a proton trapped inside the atomic nucleus, where the proton is free to move inside the nucleus anywhere it likes, but it has an enormously huge potential energy outside. So the physical situations would be one where a particle is free to move in a certain region in space, but is completely forbidden from moving outside that region.
Okay. Thanks a lot. And thanks for the link, Matt. I'll check it out.
Uh, what did that post?
Yeah, I just saw it. I don't know where it is.
There we are. Yes, thank you, Matthew. I guess there's a lag on my end. Um, yeah, so there are some physical situations that this describes reasonably well. But you're right, this is kind of a toy problem. This is one that even I can do the algebra for without messing up. And what we're going to do is we're going to go to gradually more complex potentials. Not complex like complex numbers, but complex as in harder to do the algebra for, and kind of gain skill in doing these calculations, and then over time, um, kind of build up an understanding of how more physical systems will behave. And the ultimate goal is the one that I talked about before. Ultimately, we want to understand the hydrogen atom. But to do that, we have a thing moving in 3 dimensions. So what we're kind of doing is we're dealing with like more and more sophisticated situations that apply to more and more physical systems, and building up to understanding the hydrogen atom. Is that useful?
Yes, thank you.
Sure. And again, like Anytime, please turn on your mic and interrupt me and ask questions. Like I want to hear as much of your voices as you all want to share with me. So, continuing where we were, we know that I should switch back to my pencil tool. We know that psi of x is some amplitude times the sine of kx, but we now know what k is. That's the sine. K is n pi over L. That formula may look real familiar to those who took physics of music or physics 307 with me. But we can do even one better. So these are the wave functions for n equals some integer. But an interesting thing here is the energies of these states. So we found their wave functions. We'd also like to know what their energies are. So how might I find their energies? I'll scroll back to the previous page of notes if anybody has a suggestion. So if nobody has a suggestion about how to find the energies, so let me ask this. Would it be useful for you all, we've done a lot of mathematics, would it be useful for you all for me to like review in words what the significance of each step that we took was? Okay, so we'll do that, Charles. So here is what we have done. Again, if you're ever like not following something, please let me know because I can't look at your faces and kind of see and judge how well people are following. And I've also never taught this material before. So if you're ever not following something, please let me know, and I'm very happy to review. Um, so we've done several steps in realizing what our wave function must be. The first thing we did was we saw that psi of x must go to 0 at x equals 0 and x equals L. The second thing we did was we said inside the well we have that as the Schrodinger equation, and that tells us that psi of x must be sine or cosine. And then we rejected cosine since the cosine of 0 is 1, and that disagrees with the first thing that we concluded. And then we said that a generic sine function is psi of x is some amplitude times the sine of some wave number times x. Then we realized that there are certain constraints on what k must be. Oh, actually, there's one other thing that we did in there. Then we have the second derivative of a sine kx equals a sine kx. And by doing this, we can solve for e equals square root 2me, oops, no, k, sorry. K is 2me over h bar. So we realize there's a connection between the wave number and the energy. Yanju asks, could we modify something from Young's model to get the energy? I'm actually not familiar with Young's model. Young's model for what exactly? Could you explain what that is? Well, he's typing what Young's model is. I'm going to list a third point. After we did those things, after we figured out that our solutions, oh, k equals EA. Oh, you mean Young's modulus. So here, so Yanju has referenced something from Physics 307, where he's written this equation that we used for a vibrating string. So Yanju, the problem here is that there are more things in physics than we have letters. So when this equation came up before, E here was not energy, this was Young's modulus, which is related to the stiffness of a substance, and K here was not wave number, K here was the spring constant. So it's true, right? We have now something with K's and E's in it, but the trouble is that we ran out of letters in the alphabet and had to start reusing letters. So physics can be very confusing when we use two different letters for the same, one letter for two different things, but our alphabet is only so big. So the next thing that we did was then we said, all right, but psi of L is 0 also. So this constrains the values of K to only those where sine of Kx, of Kl equals 0. So the only values that have a sign of 0 are integer multiples of pi. So this gives us that K equals, KL equals n pi. So this is KL, or K equals, KL is n pi. So K is n pi over L. And if we put this back in, we get psi of x is a sine n pi x over L. So Charles, you had asked for a recap. Is this recap useful? Okay, good. Any other questions or comments so far? Okay, so what I want to do now, the thing that I was kind of prompting you for, and the thing that kind of made me say, hey, we need to do a recap, is that I have this relationship, which I'm highlighting in yellow now, between the wave number k and the allowed energy. So I'm going to go again to my next page. I'm going to grab this picture, stick it down there as well. So we can identify these various stationary states with a value of n. So the one in green is n equals 1, the one in pink is n equals 2, the one in light blue is n equals 3, and so on. Danielle asks, if k equals n pi over L, then we can use particle wave momentum to solve for the energy. Yes, so Danielle, I'm not going to invoke momentum exactly, but if you were to, I'm going to do what Nick tells me to do, but if you say that momentum is mass times velocity, kind of using some pseudo-classical ideas here, and the kinetic energy of something is 1/2 mv squared, then the kinetic energy is p squared over 2m, and following that strand of thought, Danielle, gets you the same value. So yeah, like what you're proposing is completely valid. And we'll actually come back to this idea of the thing inside the potential well being essentially a simple harmonic oscillator. Or no, sorry, not a simple harmonic oscillator, a free particle. Nick says set the two equations for k equal to each other. So if k equals, looking back up, n pi over L, and k equals square root of 2me over h bar, then n pi over L equals square root 2me over h bar. Squaring both sides gives me, because what we want to do is we want to solve for the energy. That gives me n squared pi squared over L squared equals 2me over h bar. And E equals n squared pi squared h bar over 2m L squared. I'm going to draw a big honkin' red box around this formula. Is it not h bar squared? It is. It is not h bar squared. Wait a minute. Did I? Yes, I made a mistake in my formula for k. Thank you. You're right, Nick. I got the wrong answer. So if I look back up here, let me go back and check. So in my expression here for k, I have yes, it looks like I have, yes, I dropped a squared here. Thank you so much, Nick. That matters. So that means anytime that formula has appeared, it has been incorrect. I am so sorry. That's h bar squared. This is h bar squared. That's h bar squared. And that is h bar squared. Thank you, Nick. So what this tells me is that if I have a particle, I mean, let's go back to the big idea. If I have a particle stuck in a box, um, it has only certain allowed energies, and that's an unexpected thing. And this is true, but we saw this when we did like the simulations of the drumhead that I showed you. We saw that there are only certain vibrational frequencies corresponding to stationary states that this thing is allowed to vibrate in. But that's kind of not what you expect in classical mechanics. Let me give you a bit of an example. Well, yeah, let's talk about a bunch of examples in one. So in classical mechanics, if I have a system that's oscillating back and forth, then that system can have kind of any energy it likes. So as an example, if I imagine two atoms oscillating back and forth, maybe they're chemically bonded, then if I make a plot of energy, make that straight, versus the radius that they are from one another. So if I've got something like this, here's another atom, and they are oscillating back and forth, then I can plot the potential as a function of their separation as a function of that separation. And schematically, that potential looks like this. So again, it's potential energy on the vertical axis and radius on the horizontal axis. So if I say give the particles a certain energy, right? If I say, call this the energy of the particles, E, then what that means is that the particle can never have more potential energy than it has total energy, right? So can never have more potential energy than total energy. So that means that our two atoms are confined to never be more than that distance away from each other. These are called the classical turning points. We'll see in quantum mechanics that this is not necessarily true. This is true classically, not in quantum mechanics. They're called the turning points because if I have these two atoms bouncing back and forth, when they get to that radius away from each other, they will turn around. Like the turning point literally means it turns around here. But the other thing that is true, well, let's make a table. Let's make a comparison table here. So in the classical way of thinking about this problem, the quantum way of thinking about this system, a couple of behaviors are a bit different. In classical land, the particles never go past the classical turning points, but in quantum land, you've probably heard of quantum tunneling. We haven't gotten here yet, but we will see it soon. The particles can tunnel past the classical turning points. We haven't seen mathematically how that happens yet, because in our system, the potential confining the particle into the well was infinitely strong. But when we relax that and make that a finite potential, we will see tunneling, like here. Also, in classical land, the particles can have any energy, but in quantum mechanics, only certain energies corresponding to stationary states are allowed. Oh, what I mean past, I mean physically beyond. So, in this example, that's not what I want. Nope. Get this right in a moment. In this example, stop drawing a square. I want a rectangle. Hang on. Sorry, I'm still learning how to use this tool. Well, we'll just shade it. Yeah, that didn't work either. Sorry, folks. I'm still new at this. This region over here that I'm shading in green in a very unsophisticated way, and this region over here that I'm shading in green, these are classically forbidden regions, because for the particle to move into those regions, we'll label them classically forbidden, it would have to have more total energy than it had potential energy. And like if I have 10 joules of potential energy, and 8 joules of total energy, that would mean my kinetic energy is negative. And kinetic energy cannot be negative in classical physics. It turns out kinetic energy can, in a sense, be negative in quantum mechanics, and that's what we'll see soon. So you you will now have the solutions for the classical square well, or the quantum infinite square well, which are these. So there's the energies. Whoops, that's the wave number. And the wave functions were that psi of x equals a sine n pi x over L. You can find a by using the normalization constant. Yes, I can, Vaishnavi. So this is kind of on Tuesday. One thing that I want to announce before I forget, and I'm sorry I'm kind of scattered. I've been teaching since very early this morning. Your homework is extended. Your homework that is listed as being due next Wednesday is instead due next Friday. So you all are getting a 2-day extension on your homework because all of the things that you need for your homework, we're not finishing in today's class. I ran it by Jack, it's okay. So our plan for next week is on Tuesday, I will finish getting you all of the information that you need. And then on on Tuesday you'll get all the information you need, and then you have until Friday to do your homework. Then next Thursday, instead of having the exam, as long as I go by my plan, on Thursday we will have a guest class on the physics of nuclear reactors, radioactive decay, and nuclear explosions. And I will say everything that I know about making bombs, which is not that much. So Vaishnavi asks, can I elaborate a little bit more on why negative kinetic energy is possible? So it turns out that we have this relationship. And this will be the last thing we do today. So we know, let me get it right, that K is square root 2me over h bar. H bar squared, which is what I forgot earlier. You know that for a free particle, its wave function, and I'm going to list psi of x and t here, is e to the ikx times e to the minus I omega t, where k is given by this, and omega is given by e equals h bar omega. But now what I'm going to do is I'm going to write down the Schrodinger equation with the potential energy term back in. I may run 2 minutes over answering your question, Vaishnavi. I'm very sorry. So I have... Try to go fast. Equals e psi of x. So if I imagine that what I'm going to do is I'm going to move everything to the right side. So I'm going, and this is how we will start class next time. So Vaishnavi, your question is a perfect segue into Tuesday. This gives me minus h bar squared over 2m d squared psi dx squared equals e minus u of x psi of x. So what that means, suppose I have a particle moving in a constant potential. If u is greater than e, then I have, again, I'm being sloppy because I'm in a hurry to let you all out on time. This is a negative value times psi of x. And what that means is, remember when we solved for k, and we saw that gives you, and again, we're coming there next time, but you can probably imagine how this goes. This is e minus u, or e all over h bar squared. And this gives an imaginary k, and our expression for kinetic energy, so this whole thing is just the kinetic energy, becomes negative. We will talk about this more next time. So Vaishnavi, I know that's a not very satisfying answer, but I'm out of time. Thank you all for staying 2 minutes past. I can hang around for a bit more if there are any more questions. I would appreciate any feedback that you have. For me, it looks like I may be teaching this class a little longer term than I thought, because Jack is still under the weather. But please give me any feedback that you have about how well this works. I will post slides, videos, everything. And I'm going to put it on my Physics 211 website, but I will send it out as an email to the whole class. Sure, Nick. I did see your email about the thing for the Marines. But what's your non-physics question? I'm going to stop the recording here.